Good day. For those of you who do not know me, my name is Douglas Harder, and this topic we're going to look at gradient descent. So in this topic, we will describe why we may not want to use one of the two previous algorithms. We'll discuss the idea of the gradient. We will see how the gradient can indicate which direction we should be searching, and we will then see how we can use this to convert an n-dimensional minimization problem into a one-dimensional minimization problem. We will conclude by discussing issues with estimating the gradient. Now, we've already seen a number of algorithms for approximating the minimum of a real valued function of a real variable. We've also seen how we can use Newton's method to approximate or find the minimum by calculating the gradient and the Hessian and solving the resulting system of linear equations. If, however, we cannot calculate the Hessian, we could revert to using the Hooke-Jeeves method. However, this only searches in the directions of the canonical unit vectors. Is there not perhaps a better choice? Consequently, suppose that the function is sufficiently differentiable that we can calculate the partial derivatives in each of the directions. Can we use these partial derivatives to develop a better approach that gives us a better direction in which we should be moving? Well, that's what we will explore. So for a sufficiently differentiable real valued function of a vector variable, we may define the gradient as a vector that consists of the partial derivatives of that function with respect to each of the dimensions of the vector. Now, we can also normalize this gradient vector by dividing it by its 2 norm. And you will recall that we denote a normalized vector by adding a hat to that particular vector. So here is how we will represent the normalized gradient vector. All right, now the significance of the gradient is as follows. If we were to evaluate the gradient at a point u sub k, this gives us the direction of maximum increase of the function at that point. Okay, so if we have a very small value of epsilon, this essentially says, starting at the point u sub k, if we take a small step in the direction of the gradient, then the value of the function will be greater than taking a small step from that point u sub k in any other direction. Similarly, for a sufficiently differentiable function, the opposite direction of the gradient gives us the direction of maximum decrease. So if we are trying to find a minimum, one of the most logical directions to move then is in the direction of maximum decrease. So if we are at a point u sub k and we take a small step in any direction, then the step in the direction of the negated gradient will result in a value of f that is smaller than taking an equally sized step in any other direction, recalling that u sub k or u hat could be any unit vector. Now, mathematically, this is essentially saying that the slope in the direction of the gradient is greater than or equal to the slope in any other direction. So if we are moving in the direction of the gradient at a rate alpha, and then we differentiate the rate of change of the function with respect to alpha as we move in the direction of the gradient, then the rate of change of the function is going to be greater than or equal to any other rate of change in any other direction. Also, the rate of change of the function as we move in the direction of the gradient is equal to the 2 norm of the gradient. So we know that moving in the direction of the gradient gives us the greatest rate of change, increase, and we know that the rate of change in that direction is the 2 norm of that gradient. All right, now let's consider the following bivariate function, that is a function of 2 variables, or equivalently a function of a 2-dimensional vector. I could write this as a function of u sub 1 and u sub 2, but that becomes difficult to differentiate between the various variables, and so instead I will write this as a function of x and y. However, we should realize that this is essentially a function of a 2-dimensional vector. This particular function has a unique minimum at the point u is 2, 0. That is, x is equal to 2, y is equal to 0. And in the bottom we see an image on the left-hand side of the function as a function of x and y, and you can see the unique minimum. And on the right-hand side we have a contour plot. So all of the points on a line, or one of those concentric ovals, has the same value of the function. And you can see that they center around the unique minimum. Again, because this is sufficiently differentiable, those contours are smooth, continuous, straight, differentiable lines. The contours on the right equal the contours on the left. Now, for this particular function, we can calculate the gradient by differentiating with respect to x and y, and we get that the gradient is this particular vector-valued function of a vector variable. If we have the point u is equal to 1, 2, we can calculate the gradient at this point. Specifically, the gradient at this point is -3, 4. We can also therefore calculate the normalized gradient vector, and that would give us a vector in the direction of maximum increase that is also a unit vector. So in this case, the normalized gradient at the point 1, 2 is -0.6, 0.8. Again, at every single point, the gradient is likely going to be different. Viewing this visually, on the right-hand side, we have the contour map and the point 1, 2, and the gradient, which is a vector -3, 4. As you can see, at this point, we are moving away from the minimum. That is, we are going in the direction of maximum increase at that point. Now, on a contour line, every single point is at the exact same height. So if you were walking along a contour point or along a contour line, you would not be changing your elevation. The gradient, however, would therefore be perpendicular to these contour lines. And as you can see here, it does appear that the gradient at the point 1, 2 is a vector that is indeed perpendicular to the closest contour line. On the left-hand side, we can see the point and the gradient, and you can see that this gradient does approximately point us in the direction of maximum increase. However, at this point, I've also given the arrow a slight increase, indicating the rate of change of this particular gradient vector at that point. So again, if we are moving in the direction of the gradient, we are moving in the direction of maximum local increase. All right, so if we are at a point u sub k, and we then consider points u sub k plus alpha times the normalized gradient at that point, then for alpha greater than 0, this moves us in the direction of steepest ascent. However, we're looking for a minimum, and therefore, if u sub k plus alpha times the normalized gradient moves us in the direction of steepest ascent, then u sub k minus alpha times the normalized gradient vector for alpha greater than 0 moves us in the direction of steepest descent. So the opposite direction of the gradient is the direction of steepest descent. But as you can see in this simple example, the opposite direction, or the negation of the gradient, doesn't point us directly at the minimum, but it does point us downhill. Thus, if we start to at least move in this direction, we should be moving towards at least a local minimum. All right, now notice that from the previous slide we saw that u sub k minus alpha times the normalized gradient, that essentially defines a line in r to the n. There's only one real variable alpha. Consequently, if we evaluate the function at points on this line, this simply becomes a real valued function of a real variable. And you'll remember we just spent a number of topics looking at different ways of approximating minima of a real valued function of a real variable. So, for example, in the case that we've been looking at up until now, recall that at the point 1, 2, the gradient of the function was, when normalized, negative 0.6, 0.8. So subtracting alpha times this normalized gradient vector from 1, 2 gives us this vector. We can now evaluate the function at this point, or at the points on this line, and you'll notice that that gives us, in this case, a quadratic function in exactly one variable alpha. Well, we can now find a minimum of this quadratic function in alpha. All right, once we find the gradient at a point u sub k, we have one of two possible strategies. The first one is to simply move in the direction of the gradient and then try again. Calculate the gradient at the new point and then try again, at each step recalculating the gradient. A second approach is to calculate the gradient once and then move in that direction until you find a local minimum along that line. At that point, and only then, do you try again calculating the gradient at that minimum and then move in the direction of the new gradient. The analogies are as follows. We are determining the direction of steepest descent, and in the first case, simply taking one step in that direction. In the second, we are moving in that direction until we start going uphill again. Now, if we take only a single step in the direction of the gradient and then recalculate the gradient, this may actually require significant computational effort at every single step. Also, we have another issue, that is, what is the optimal step size? After all, if the step size is too small, then we may be calculating the gradient many times. However, if the step size is too large, we could actually find ourselves on the other side of the valley. Now, with the second strategy, we're searching in the direction of the gradient. That is, we are searching along a line. We've calculated the gradient once, but now we are minimizing essentially a real valued function of a real variable. So we've converted an n-dimensional problem into a one-dimensional problem. We've already looked at a number of algorithms for approximating solutions to finding a minimum of a real valued function of a real variable. Now suppose we adopt this second strategy. So given a point u sub k, we calculate the gradient and then search along that line until we find a local minimum along that line. This gives us a point u sub k plus 1. So at this point, we're going to calculate the gradient again. And something that you're going to find interesting, and if you think about it, not too entirely non-intuitive, the gradient at this next point should actually be perpendicular to the gradient we previously calculated. Now, how do we find the minimum in this direction? You'll recall previously, whenever we were finding the minimum of a real valued function of a real variable, we assumed we already had an idea as to where the minimum was. But now all we're doing is calculating the gradient and, well, moving in that direction. How far do we move? Are we going to be moving a significant distance or only a very short step? Well, there are strategies that can be used, and you can look these up online or in any textbook, but we're going to focus on making one additional assumption that allows us to take a shortcut to finding that local minimum, even if it is very far away. So the two assumptions we're going to make is that, first of all, the function has a unique minimum and that function is concave up, meaning if I take any 2 points on the surface and draw a line connecting those 2 points, the value of the function is always less than any point on the line connecting those 2 points. Also, we're going to assume that the function in any direction ultimately goes to infinity. Now, what's really nice is if these conditions are true globally, then these conditions are also true on any line that the function is defined on. Specifically, the point we are at minus alpha times the normalized gradient vector. Now, if the conditions we assumed are true, what we will do is we will begin by calculating f evaluated at the point u sub k minus phi to the m times the normalized gradient vector. And we will start with m is equal to 0. So this is just u sub k minus the normalized gradient vector. You'll recall from the golden mean search that phi is the golden ratio 1.618. Okay, now we continue either incrementing or decrementing the value m until we find 3 points, capital M plus 1, and capital M minus 1, such that the value of the function at u sub k minus phi to the capital M times the normalized gradient vector is less than the function evaluated at either u sub k minus phi to the m minus 1 times the normalized gradient vector, or the function evaluated at u sub k minus phi to the m plus 1 times the normalized gradient vector. In this case, we can now just continue by using the golden ratio search, which we've already described, starting with the interval from phi to the m minus 1 going up to phi to the m plus 1. We would take one step of the golden section search, having already calculated 3 of the 4 values, and after this we could continue with, say, the Brent-Dekker method. All right, so in our example we'd proceed as follows. First of all, we'd evaluate the function at u sub k plus the normalized gradient vector. Seeing that we're going downhill, we'd evaluate the function at u sub k plus phi times the normalized gradient vector. We're still going downhill, so once again, now the u sub k plus phi squared times the normalized gradient vector. Still going downhill, but with the next step, phi u sub k, the function evaluated at u sub k plus phi cubed times the normalized gradient vector gives us a point that is now increasing. Consequently, we're guaranteed that the minimum along this line must be somewhere between alpha equaling phi and alpha equaling phi cubed. We can now apply the golden ratio search. As we've already calculated at 3 points, we only have to calculate the 4th point, and we can begin to focus in on finding the, or approximating the minimum along this line. Now, what's nice about this technique is that phi raised to the power m grows exponentially. So even if the point is very far away, so maybe alpha is 1,000,000, well, that's okay. Log base phi of 1,000,000 isn't larger than 30, so it would only take 30 steps. Then we'd start focusing. Then we can focus in and more quickly find that local minimum in this line. Now, some caveats to this algorithm. First of all, should you always start with m is equal to 0? That is, should you always start with the current point plus or minus the normalized gradient? And the answer is actually no. In general, after the first iteration, you should probably start with the previous m you found for subsequent iterations. After all, if you are only moving a distance of 0.1 times the normalized gradient with one step, chances are with the next step you will also only be moving approximately 0.1 times the normalized gradient. Now, this isn't always the case, but it is generally an assumption that may not be that unwise a choice to make. Another issue is that as you are approaching the minimum, it may happen that the range of powers may actually include a sequence where the value of the function is equal. Remember, with any function for which we are finding the minimum, because the minimum is generally quadratic for a sufficiently differentiable function, therefore there are going to be very many points once the floating point numbers are truncated that may actually have the same value. So as we get closer and closer to the minimum, there may actually be 2 powers of phi to the capital M sub 1, going all the way up to phi to the capital M sub 2, such that the value of the function at these different points are actually all the same. So this too will require some additional attention to detail. Most likely this is going to be the minimum or very, very close to that minimum. All right, so now we've discussed strategies for using the gradient to find the minimum. Now let's actually discuss calculating or estimating the gradient. Now, in general, if we are using automatic differentiation and we used automatic differentiation to calculate the gradient, chances are we can also use automatic differentiation to calculate the Hessian. Consequently, we should go back and instead consider using Newton's method. However, it may be, even if you are using automatic differentiation, the function may not be sufficiently differentiable to calculate that Hessian. It may be sufficiently differentiable that we can calculate the gradient, in which case we would use that gradient and then use the previously described technique. However, if automatic differentiation is not available, we can still estimate the value of the gradient. After all, the gradient is nothing more than a vector of partial derivatives. Now, again, this is going to be possible if the solution is differentiable near the extremum. So all of this gradient descent discussion only applies if the solution is sufficiently differentiable. Consequently, we will be able to calculate an approximation of the gradient and move in that direction. Now, to approximate the gradient, recall that the vector E sub k is how we represent the kth canonical unit vector. That is, it is the vector where all entries are 0 except for the kth entry, and that entry is equal to 1. So in this case, we can calculate the kth entry of the gradient by calculating f evaluated at a vector u plus h times the kth canonical unit vector minus f evaluated at u minus h times the kth canonical vector all over 2h. Now, recall our example. We had the function f, a function of a real valued function of a two-dimensional vector described as follows. And we calculated the gradient precisely using differentiation and evaluating it at, say, a point 1, 2. Well, we can approximate the gradient by having a value of h equaling 0.01 and then approximate the two entries of the gradient. So first, the first entry is the function evaluated at 1.01 and 2 minus the function evaluated at 0.99 and 2, all over 0.2. This equals, if you were to calculate it out, exactly equals -3. We can do the second entry of the gradient as well, and so we evaluate the function at 1 and 2.01 and subtract that from that the function evaluated at 1 and 1.99. Again, all divided by 0.02, and for this we get exactly the value 4. Now you're wondering, these are not approximations, these are the exact values of the gradient. Why is that? Well, you should recall that the error of this approximation of the derivative depends on the third derivative of the function. But wait a second, this is a quadratic, so the third partial is always going to be equal to 0. So for this very specific function, using the approximation formula for the derivative actually does give us the exact answer. However, if we had a cubic or a quartic or a trigonometric or exponential function, then this would definitely not be the case. We would only be finding an approximation of the gradient, not the gradient exactly. Now, is it safe to use an approximation of the gradient? Well, recall that at a minimum, there's going to be an entire region, not just a single point, where the truncated floating point values are actually equal to the truncated floating point value of the actual minimum. There will also be a much larger region where the value of the function is exceptionally close to the actual minimum value. Thus, we are still going to very likely find a good approximation of the minimum value, even if we don't necessarily have that an ideal approximation as to where the actual minimum is. So if we just want to find the minimum value, these techniques should work. Following this topic, you now understand the idea of gradient descent. That is, if the gradient of a real valued function of a vector variable is calculated, it points in the direction of maximum increase at a point. Consequently, at that same point, the opposite direction, the negation of the gradient, points in the direction of maximum decrease. You understand that we should then use algorithms we've already looked at to find a minimum in that direction. You are aware that using this approach reduces the number of times that we must actually calculate the gradient, which is an expensive operation, and thus this is reasonably efficient. You also know that you can approximate the gradient by using finite difference formulas, and that these approximations of the gradient are still likely to be sufficiently accurate to help find any local minimum. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!